So I would like to welcome everyone to this session on transient classification. We have on the agenda 4 talks. So that would be Daniel, Paula, Konstantin, and Ashley, who are going to talk to us each about a 3 minutes presentation. So for the questions, you can put your questions on the Slack channel or on the Zoom chat, and we are going to take questions only after everyone has finished. Okay. So for the speakers, keep an eye on me. I will let you know when you have 2 minutes left. We're going to be very strict on time because we have to go through this in the correct time. Okay. Just a reminder that we all agreed with the code of conduct for the Rubin Observatory. So just remind of what is written there, and we should all keep in mind the requirements of the code of conduct. And also for showing appreciation, the videos are going to be posted, and any feedback you want to give us, it's better if you give it on chat on Slack, and I will ask the questions that you post after the presentations. So I think for now we can start. So the first presentation that we have today is Daniel. So Daniel, if you want to start, I will let you know when you have 1 minute left.
Okay, great. Hopefully everybody can hear me okay. So I'm going to be talking about what we're doing with this Wiki Transient facility, partially in preparation for what we hope to do in a few years with Rubin Observatory. Of course, we're all looking forward to the great things that Rubin will do. In the meantime, we have existing surveys, and in particular, we have the Wiki Transient facility, which is a transient optimized survey using a smaller telescope, of course, 1.2 meters, but with a bigger camera, 47 square degrees. So this reaches about a limiting magnitude of 20.5. It has a dedicated follow-up spectrographic system. So one advantage of going shallow and wide is that you can actually get spectra of most of your transients and classify them. So the ZTF is doing many different things, many different surveys, some high cadence, some asteroid optimized, but its biggest project, which is funded by public NSF funding, is called the Northern Sky Survey. And it's a survey of about 18,000 square degrees over 3 nights in GNR filters. And as many of you know, the alerts that are produced from this survey are, in a very similar way to what LSST will do, sent to public brokers for everyone to use. Okay, we can go to the next slide.
Next slide, please.
I changed the slide. Don't you see the next slide?
Okay, it's just, I guess it's just lagged a little bit. Yes, I see it now. Okay, thank you. Okay, so as to what we're doing, so because we have this spectrographic follow-up capability, as well as other spectrographic facilities around the world, we are trying to do a magnitude limited survey with the public data products. And so the goal of this survey, which is called the Bright Transient Survey, is first of all to register all transients that peak above 19th magnitude and classify all, or almost all of them at least, that ever reach brighter than 18.5 magnitude. This has been going on for a little over 2 years. And as of this week, we've confirmed over 3,000 supernovae of various types, as well as significant numbers of more obscure transients as well. And based on our current calculations, we're about 93% spectroscopically complete for transients which are not occurring during coverage gaps or are about to set or just rising, et cetera. And as I said, because the alerts are online, this also allows access to the light curves, and our transient classifications are being sent to TNS. Okay, we can go to the third slide now.
I changed the slide. There's probably a delay.
Okay, there we go. Part of the image was missing. Okay, so yeah, so this is available for everyone to use. We'll have some papers out on it soon. But in the meantime, we are doing some basic analysis using things like durations, which we can measure from the light curves, peak luminosities. And already with a sample like this, which is spectroscopically validated, you can see that different classes of transients, whether those be type 1As, type 2s, or more exotic things, do seem to prefer different regions of phase space in these parameters and have different trends. And so although currently we're not trying to do anything like light curve classification, we think that this complete spectroscopically validated set will be a very useful resource for developing tools for the Rubin era. You can explore the properties of our sample at these 2 links below, and you can read a little bit more about the survey in the paper listed here and in future papers that will be out soon.
Okay, thank you, Daniel. So remember to put questions on the Slack on the chat, okay? Our next presentation.
Is just me, or I'm not hearing Emily?
I'm having the same problem.
Yes,
Okay,
I couldn't hear Emille either.
Okay, so I will start.
Okay, so yeah, so the second
start.
talk is
Please
Paula
start.
Sánchez Sáez on the ALERCE Light curve classifier.
Okay, thanks. So today we present the ALERCE Light curve classifier. ALERCE is a Chilean broker designed for the rapid and efficient classification of transient and variable objects. We have 2 models, the stamp classifier that is going to be presented by Francisco Foster in a parallel session. And today we'll tell you about the light curve classifier. So this model is designed to classify streams of alerts from different surveys, including the ZTF survey, and in the future, the LSST. So this model classifies all the sources with 6 or more alerts in a given band, and is called balanced hierarchical random forest because we have a 2-level scheme, where in the first level, we classify each source as transient, stochastic, or periodic, and then we further resolve each of these classes. Oops, sorry. What happened? Something happened with the...
That was me, sorry.
Okay, can you go back to the previous slide, please? No, that's... Okay, that one.
The next
Thanks.
one?
Yeah, no, that one. Thanks. So then we, in a second level, we further resolved each of these broad classes into the different classes of supernovae, different classes of active galactic nuclei, and periodic variable stars. And now you can go to the next slide. Okay, so this model used several features. Now, in this current version, we have 152 features where we used detections from the ZTF alert stream. That means all the sources with a 5 sigma detection in the difference images. And including in this set of features, we have features to model supernova light curves to find multi-band periods, and also features relevant for the classification of stochastic sources, like the irregular autoregressive model and the Mexican hat power spectrum. And these 2 features in particular are novel, so I recommend you to go to the paper and take a look at them. We also have non-detection features that use all the images without a 5 sigma detection, where a limited magnitude is reported. And we also use colors from other surveys like Bytes. So all these features are designed in a way that are now implemented in the ZTF alert stream, but can be used in the future for LSST. Next, please. Next slide. I don't see.
There was a delay there, but I changed the slide.
Okay, thanks. So here you can see the results of the current version of the model. In the left images have the confusion matrix. You can see that it's quite diagonal, but we still have some confusion remaining for the different classes of supernovae. We are working now on improving this using, for instance, data augmentation. In the central panel, you can see the number of classified sources, considering all the sources with 6 or more alerts in the ZTF stream. Most of them are classified as periodic sources, and the classes with the lowest number of candidates are the supernovae classes. And finally, in the right panel, you can see the galactic latitude of extragalactic candidates. and they're G-R colors, and you can see that most of them are located outside the galactic plane, and the ones in the galactic planes have lower probabilities and also redder colors. So this paper was just published today in the archive, so I invite you to go there. If you click in the name of the here in Sánchez Sáez about 2020, you will go. You will see the link for the archive. So thanks.
Thank you, Paula. So next one is Konstantin.
Yes, hello. I don't see text. Okay. Is it there still?
Yeah.
Oh, great. Okay, hello. My name is Konstantin Malanchev. I'm during a transit from Lomonosov Moscow State University to University of Illinois, Urbana-Champaign. And today I'm going to present you preliminary results of the third SNET project workshop, which took place in early July and was dedicated to find anomalies objects in ZTF DR3. Thanks, Daniel, to introduce ZTF projects, so I can go right to my topic. We use machine learning approach to select a couple of hundred of the most wide light curves within over 2 million ZTF objects. Then we manually examined these couple of hundred objects using all publicly available data we could find. This yields us a lot of interesting unusual objects. For example, here you can see transient candidates, some of transient candidates we found, both with previously known and unknown classification. For instance, bottom right is probably nova-like object. Using external data sources, we found that it had 3 outbursts, including this ZTF1, during only 2 years, which makes it very strange, very recurrent novae. Moreover, we probably found some known as bottom left and unknown and previously unknown supernova 1A candidates. Please, next slide. And while changing, I would like to say sorry, I forgot to add a legend to my figures. So colors correspond to passband, green is G, red is R, and black is I, 3 passbands of ZTF. So here we see some examples of variable star candidates. Previous slide, please. Can you return previous slide? So there are yes, this one. Thank you. Here we can see, for example, in top left, luminous blue variable candidate, which has unusual variability for these kind of objects. And another interesting example is bottom left is a Cepheid candidate. And you know that Cepheid is an important part of cosmic distance ladder. But this Cepheid is in galaxy, is located in galactic halo, which makes it a possible low metal population to Cepheid, which are not so common. Next slide, please. The final slide with examples of objects that we couldn't classify yet. For example, these top light curves, show outlier observations, which could be a sign of a very fast variability, which could be very interesting. Of course, all objects on this slide could be examples of some very not obvious, very wide artifacts. Oh, 3 minutes is over, yeah? Yeah. Okay, so I go to the end. So anomaly detection methods as unsupervised machine learning can give very interesting astrophysical results without any prior information, but of course we need to do some astrophysical work to identify these objects. Please see our research notes paper for more details, and thank you for your attention.
Thank you, Konstantin. So our next speaker, Ashley, are you there?
Yeah, can you hear me?
Yes.
Yes. Okay, excellent. Yeah, so my name is Victoria Ashley Villar. I'm a new Simons Junior Postdoctoral Fellow at Columbia University and the Center for Astrophysics at Flatiron. I'm telling you about a paper that I will submit to archive at 2:01 during this session. So it's out very soon. In particular, it'll be one of 2 companion papers, one by myself and one led by Griffin Hosenzade, both at most of this work was done at Harvard, where we present a few results, and each of my slides will kind of just highlight one of them. The first, if you're interested in supernovae, we're releasing a large data set of about 5,000 supernova-like transients that were detected during the Pan-STARRS Medium Deep Survey. So this is a survey that was conducted over the course of 4.5 years, from 2010 to 2014. And during this, well, this survey is interesting because it has very similar colors and cadence to LSST, although about 1/1000th of the discovery rate that LSST is expected to have. Of these, we have about 560 spectroscopically classified supernovae that we will release. And we have about 3,000 reliable redshift host measurements for these supernovae. And you can go to the next slide. So also as a part of this paper, we will be releasing a new photometric classifier, which I have named SuperRAENN. I promise there's a picture there. Okay, it is a little bit complicated to describe exactly how this algorithm works, but if you're a machine learning person, you may be interested in this because it's a fairly novel neural network architecture that specifically uses something called an autoencoder architecture with recurrent neurons. So the idea is that just like as you type into your cell phone and it tries to guess predictively what you would like to say next, this recurrent autoencoder will actively try to predict what the supernova light curve will look like, and in doing so, extract data-driven features. So we use a combination of these data-driven features and hand-selected features to classify all of the supernova-like transients that we will be reporting, which have spectroscopic redshifts. So that table of probabilities will also be released in this paper. And also this new code with this new architecture called SuperRAENN is available via GitHub and also to pip install. You can go to the next slide. And finally, although not entirely the point of this paper, but what is our next extension is that we'll be working with this same code base to apply it to live streams of data from ZTF to actively classify supernovae in real time. And here, one of my only pictures I'm showing you on the right is a light curve of a spectroscopically classified type 1a supernovae, and the data points are being shown as circles. The lines are actually a model that comes out entirely of our autoencoder. So there's no physics in this model, and it's not interpolation. It's entirely from using all of the data to figure out what it thinks the underlying model looks like. That's it. Thanks.
Thank you very much. I'm going to stop sharing because I think I have some connection problems. We have a few questions. Márcio, do you have questions?
Yes, so we can start with some questions. So Guillermo Cabrera wants to ask Konstantin, how do you qualitatively evaluate your model in terms of how good it is in detecting outliers? Quantitatively, actually.
Yeah, it's a really good question. So we thought what type of objects we are really interesting to find. Yeah, for example, we can imagine some really wide light curves or really wide objects, for example, binary microlensing events. Yeah, so we generate such objects with cadence of ZTF and tried to find them with our anomaly detection algorithm, and we found them. So we found a lot of objects, a lot of these fake objects that we generated and tried to find among real ZTF objects.
Thank you.
Very nice. Should we go ahead with another question, Emille? Or,
Yes, please. We still have a few times. So you can
all right. So there is a question from David Buckley to Daniel Perley. The question is, how does ZTF and growth interact in terms of transient follow-up?
Yeah, so ZTF and growth are slightly different things. ZTF describes the survey itself, and so that includes plenty of non-transient follow-up and hardware and everything else. Growth is a collaboration that's part education. Within ZTF, it's largely the collaboration that does gravitational wave alert follow-up, and so that's led by Márcio Catelan, and when the gravitational wave event occurs, she uses that group to coordinate follow-up around the world, but it's occasionally also used for other types of transients, but not for generic supernovae and general classifications of other things like that, which happens depending on the particular group within ZTF and exactly what the science area is.
Nice, thank you. Continue, Emille?
Yes, yes, continue.
All right, so there's a question from Thomas Miller to Paula Sánchez Sáez. The question is, how can you get such a high accuracy in classifying superluminous supernovae?
Yes, that's a good question. Actually, we were very surprised when we saw those results. And it's mainly because well, we have several features, and in particular, we have the non-detection features that makes really easy the classification of transients. So if you see the paper, you will see that the first level of the classifier, where we separate each source as transient, periodic, or stochastic, we can say very well when a source is a transient, because we have all these non-detection features. And then superluminous supernova has, the light curves are quite longer compared to the other classes of supernovae, so it's much easier to separate them from the other classes. The highest confusion is between type 1s and type 1 BC, type 1A and type 1BC, because the shape of the light curves are super similar. So currently, that's why at least we can clearly say, okay, this is superluminous supernova, but not with the other classes, we still have some confusion.
Still have time for another question?
All right, so there is another question from Guillermo.
Actually, if you see the Slack channel, they say that the new transition time is 11:15, so we have time.
That's true. Yeah, so they extended that. Thank you, Paula. Yeah. So we have time for a few more questions, I think. So Guillermo Cabrera wants to ask Ashley, how good is the classification of SuperRAENN? Have you compared it against other models in the literature?
Yeah, that's a good question. So that's the difficult thing to do in the literature right now, because models have been largely trained on different data sets. So in particular, we're publishing our own data set, so no one else has trained on this. Many models have trained on simulated data sets such as plastic and SNPCC. So these are, unfortunately, they don't actually capture all of the intricacies of real supernovae variability. So all that being said, we actually perform as well or outperform many of models that were trained on simulated data sets. Compared to Paula's results last night, we're pretty similar as well, which is nice to know, but we can do an apples to apples comparison as soon as we train on the ZTF data set.
Great. Since the time has been shifted, we have time for a few more questions, if anyone has other questions to pose to the speakers. If not, so thanks again, everyone, for showing up. We will start the next round in 7 minutes. Okay. Thanks a lot. Okay, so welcome back, everyone, to the second round of our presentations. And we are going to start with Daniel. So Daniel, please go ahead.
Okay, yeah, so my name is Daniel Perley, and I'm presenting on behalf of the ZTF Bright Transient Survey Collaboration. I think many of you have heard about ZTF, and ZTF will factor into all the talks in this session. This is the second slide. Can you go back one, please?
Sorry.
Yeah, thanks. Yeah, okay, so the Zwicky Transient Facility is a currently operating sky survey. We're all excited to have LSST up and running in a few years and all the great science that it will do. But at the meantime, we do have ZTF. It's a much smaller telescope, and so it doesn't go as deep, but it does have a bigger field, so it can cover more of the sky. And one advantage of a shallow survey is that you can spectroscopically classify the transients more easily. And because we, in particular, have the 60-inch telescope at Palomar with a dedicated spectrograph, we can do this in large numbers. I'll get back to that in a second. ZTF is doing many different science, including high cadence surveys, galactic plane surveys, asteroid surveys, but its biggest project, which is funded by the NSF, is a public survey of about 18 square degrees in 2 filters over 3-day cadence. And all the data products from this, the difference alerts, are sent in a very similar way that LST will send alerts to the community via a range of public brokers. Okay, so we can go to the next slide again.
I changed this slide.
All right, so coming back to the topic of this survey, which is, or the topic of this talk, which is the Bright Transient Survey. This is an effort that we're doing within the ZTF collaboration to use the public survey and to provide a magnitude limited sample of transients. So specifically, we are cataloging all transients that ever reach greater than 19th magnitude beyond our own galaxy, and we're attempting to classify all of them that reach magnitudes brighter than 18.5. We started doing this in the summer of 2018. It's continuing now, and we hope to continue it into the next few years. We, as of yesterday, have classified well over 3,000 transients, most of which, of course, are well-known types of supernovae, but also significant numbers of other types of transients like tidal disruption events, low luminosity transients, novae, and other things. We have been quite successful in reaching our completeness goals. So for transients that we have pre and post-peak coverage and aren't setting, we have been able to classify 93% down to the 18.5 magnitude level. In addition to having the classifications, as part of the survey, we have light curves and the full alert histories available via the brokers, and the classification spectra that we take, we are announcing on TNS and also making, in almost all cases, the classification spectra themselves available to the public. So it's a very public effort. So we can continue to the last slide. So you can do lots of science with a survey like this. I show here just a plot, for example, showing the duration as measured from the light curves and the peak luminosity as measured from the light curves and the measured redshifts for a wide variety of different transients. So you can see right away that different classes of things do tend to occupy different parts of this diagram, which is sort of your first step towards actually developing a classification tool based on this, which we'll need in the LSST area where it will not be possible to get a spectroscopically complete set of transients down to any significantly deep magnitude level. We're making these products available, publicly available as well. So if you go to these websites, you can see our catalogs and explore and cut the sample in different ways. And the basic properties of the survey are given in this paper here by Christopher Fremling et al. A second paper will be coming out soon showing our value-added metrics, and we have many other papers planned in the near future. Thanks.
Exactly on time, thank you. So, so if you have questions, please put the questions on the chat or on the Slack channel. Márcio is monitoring that. We will take the questions at the end. Our next speaker is Paula.
Okay. Thanks. Yeah. So hello everyone, I'm Paula Sánchez Sáez. I'm a member of the ALERCE Broker, which is a Chilean initiative to classify in a very fast and efficient way different sources from surveys streams like ZTF and the feature LSST. So this model has this broker has two classifier models. The first one is the stamp classifier that is being presented in a parallel session by Francisco Foster. And today I will talk about the light curve classifier. So this classifier takes all the sources with 6 or more alerts in a given band and classifies them in a hierarchical fashion, where in the first level, we have a classifier that separates the sources as transient, stochastic, and periodic. And then we further resolve each of these classes, including different classes of supernovae, active galactic nuclei, and variable stars. Next, please. Okay, so this model uses several features. We have 3 types of features. The detection features use the 5 sigma detections obtained from the difference images, including different features to model supernovae light curves, multiband periodograms, and also features that are relevant for the classification of stochastic sources. For instance, the ultra-aggressive model and the Mexican hat power spectrum. These are novel features, and I recommend you to go to the paper and take a look at them. We also use non-detection features that use all the difference images without a 5 sigma detection, and these are particularly useful for the detection of transients. And finally, we have some features, for instance, from WISE and morphology from PAN-STARS. And all these features are designed in a way that are working with the ZTF data, but in the future will also work with LSST. Next, please. Okay, so here you can see the results that we are currently achieving with this model. In the left side, you can see the confusion matrix. It's quite diagonal, but we still have some confusion remaining in the transient classes. And that's because the number of known sources is quite low. So we are now trying to implement data augmentation models. And in the center, you can see the number of classified sources for all the sources from the ZTF ALERCE stream. We classify most of them as variable stars, and the classes with the lowest number of sources are the supernovae classes. All these classes are provided on real time if you go to the ALERCE Explorer website. And finally, in the right side, you can see a plot of the galactic latitude of the extragalactic candidates versus the T-R color. And you can see that most of them are located outside the galactic plane, and the ones in the galactic plane has lower probabilities and also redder colors. So this work was just published today in the archive. You can click here in the slides and you will go to the link, or you can also see the Slack channel where I put the link to the archive. Thanks.
Okay, thank you. Next speaker is, oops, I'm sorry. Next speaker is Konstantin.
Yes, hello.
So,
my name is Konstantin Malanchev. I'll start, okay, Emily. And you? And
yes, okay, go ahead.
I'm now during a transit from one affiliation to another, from Lomonosov Moscow State University to University of Illinois Urbana-Champaign. And today I'm going to present you preliminary results of the third SNET project workshop, which took place in early July and was dedicated to find anomalous objects in ZTF DR3. Thanks, Daniel, again, to introduce ZTF projects, so we can go ahead to my topic. We use machine learning approach to select a couple of hundred of the most wide light curves within over 2 million ZTF objects. And then we manually examined these couple of hundred objects using all publicly available data we could find. And this yields us a lot of interesting unusual objects. Here you can see examples of transient candidates we found, both with known and unknown previous classification. For instance, bottom right is probably a nova-like object, and using external source, we found that it had 3 outbursts, including this ZTF1, during only 2 years, which is too often for classical nova. Moreover, we probably found some known as bottom left and unknown supernova 1A candidates. Please, next slide. Sorry, I forgot to get a legend. So here colors on plots correspond to passbands of ZTF. Green is G, red is R, and black is I. So here are examples of variable star candidates we found. Top left is a luminous blue variable candidate, which has unusual variability for this kind of object. And bottom left is a Cepheid candidate, and you probably know that Cepheid is an important part of cosmic distance ladder, just as supernova 1A. But this Cepheid is in a galactic halo, which makes it a possible low metal population 2 Cepheid, which are not so common. So it could be interesting too. Next slide, please. Next slide presents objects which we couldn't classify yet. For example, these top light curves show outlier observations, which could be a sign of very fast variability. Of course, all objects on this slide could be examples of some not so obvious data processing artifacts. For example, bottom left object is a part of a star cluster, and bottom right is a component of visual binary, and their light curve can be a result of some photometry errors of ZTF data processing. So anomaly detection methods as unsupervised machine learning can give us interesting astrophysical objects without any prior information. But we need, of course, some astrophysical work to be done to identify these objects and found some interesting one. Please see our research notes paper for more details, and thank you for your attention.
Thank you. Thank you, Konstantin. Remember to put your questions on the chat or on the Slack channel. And our next, as soon as
Hi, can you hear me?
Yes.
Yeah,
It's your
please go
first
ahead.
slide.
Okay, great. So my name is Victoria Ashley Villar. I am a postdoctoral fellow at Columbia and the Flatiron Institute. So I'm telling you very quickly about a paper that's coming out, well, that I submitted at 2 o'clock today, that will be showing up then tomorrow on Archive. That is one of 2 companion papers, which presents a series of results from the Pan-STARRS Medium Deep Survey. So I will describe the 3 main results in 3 slides. The first is, if you're interested in supernovae, we're releasing a large sample from this survey of about 5,000 supernova-like transients that were discovered over the course of the Medium Deep Survey, which ran between 2010 and 2014. What's interesting about this data set is that it actually has very similar filters in cadence and depth to LSST, although it has about 1/1000th of the discovery rate. So it's an excellent place to be to 1, look for large populations of supernovae, and 2, to train machine learning algorithms. Amongst this data set, we will have about 3,000, which have verified measured host redshift, spectroscopic host redshift measurements, and about 560 supernovae with spectroscopic identification. Next slide, please. Along with this paper in this data set, we're also presenting a new machine learning method. Sorry, next slide. Yeah, it was correct. A new machine learning method dubbed SuperRAENN, which is a new semi-supervised classifier. So if you care about machine learning, it's an interesting architecture because it uses something called an autoencoder with recurrent neurons in order to encode incoming light curves as a totally data-driven model and then reproduce said light curves. And we use this encoded light curves to generate totally data-driven features from the light curves themselves. And we use this in conjunction with hand-selected features to provide photometric classifications for the 3,000 or so supernovae, which also have spectroscopic redshift measurements. This code is also available on GitHub or pip installable. And next slide, please. Finally, this is not quite presented in this paper, but is now ongoing work. So SuperRAENN has been trained on archival Pan-STARRS data, but is now being actively trained on live streaming ZTF data. And what's really exciting to me about this architecture is that it can make active predictions of what it believes the light curve will look like in future times. And it's entirely independent of physical models, but just pre-trained on existing data. So here, one of my only plots I have on the right-hand side is showing data from Pan-STARRS, those are the circles, in GRIZ. And the line that you see is actually the model from this autoencoder that is dubbed SuperRAENN. And its prediction entirely made from just understanding what the full set of light curves looks like, and then guessing what this type 1a supernova will look like. And so, yeah, that should be on the archive tomorrow. Thanks.
Thank you. Thank you, Ashley. And thanks to all the speakers. So we have time for questions.
Yes, so we have a question from Monica Sorensen. She's asking, Konstantin, if you can explain a little bit how the anomaly algorithm is implemented and what machine learning tools you are using.
So I'll try to be very short during this answer. So we have used commonly used machine learning algorithm for these kind of task. So we generated features for our outlook, for our light curves, and used algorithm like isolation forest, Gaussian mixture model, one-class support vector machine, and local outlier factor, and some combination of their output too. All these algorithms, they are trying to use, they are trying to find some sparse part of your feature space, yes, and say that objects that are located in this sparse part of feature space are probably anomalous. So the short answer is this.
Okay, thanks a lot. So there's also a question from Chris Lintup, seconded by Michelle Luchtner. They would both like to hear more about the features that Ashley has hand-selected for photometric classification. And so do I.
Yeah, so I will say, like I mentioned in chat, they're not very interesting. There's nothing really novel coming from here. There are features such as what is the peak luminosity, what is a measurement of the rise time, the decay time of a light curve. And that's been shown, I think, even in Dan's slide, that even something as simple as making a duration luminosity plot for extragalactic transients is a very good way to classify many of these events. The data-driven features that are chosen from this autoencoder are correlated to some of these hand-selected features, but we didn't do an in-depth study of that.
Thank you. So there's another question by Monica, and she's asking Daniel Perley, what's the accuracy of classification done with SCDM?
Yeah, so it depends on the magnitude, of course. The brighter the transient is, the better the signal noise is. It also depends on if there's host galaxy contamination. With the survey we're doing, in general, if we have any reason to disbelieve the classification that's coming out of SCDM, we get other spectra later to confirm it. And so there's a bit of a circular thing in which, you know, if it's not a secure classification, then we validate it. If we think it's good, we don't bother. But in general, it is high for cases where you wouldn't need to turn to something anyway, such as cases where it's in a bright galaxy with a very strong background, or it's a very unusual class of transient with narrow lines that you have to use a higher resolution spectrograph to see.
Okay, thank you. So we have another question from Michelle. She's asking Ashley again if she used redshift information, photometric or otherwise.
Yeah, so I answered in chat again, I'm sorry. So we did not use redshift as a feature, but we have corrected for redshift. So there's a slight distinction there, but we don't use it as a feature.
Thanks. Any other questions?
I have a question following up with Michelle. So my question is for Paula very quickly. The classifier, I was inspired by the previous question. The classifier used from ALERCE, do you use any meta information, any kind of metadata for the light curve classifications?
You mean metadata with?
Like host galaxies or redshifts or anything that is not the light curve?
Currently, we don't have information from the host. We are working now on implementing that. We just received some data that will allow us to do that. But the idea of this first model is that it only use data from the ALERCE, the ZTF ALERCE, and also WISE data. So nothing related with the host, because we are not trying to bias the model. If a source doesn't have any host information, we don't want to bias the classifier by that.
Okay, thanks.
Any additional questions? I have one.
Yeah.
So I have a question for Konstantin. I was wondering, so you have a type 2 Cepheid that you identified. So how can you be sure that it's a type 2 Cepheid and not an anomalous Cepheid?
It's a good question. So our results are very preliminary, and probably we'll try to have some spectra for such kind of objects. So we think that it could be a low metal Cepheid, so we need spectra to prove it. Yeah, and we're going to have it.
So did you check to see if it's in the vicinity of any known globular clusters or dwarf galaxies? Because, you know, globular clusters have type 2 Cepheids in significant numbers in some cases, whereas anomalous Cepheids are present in large numbers in dwarf galaxies. So that might help understand their nature.
I believe it is not a global cluster or dwarf galaxy, this one, yeah, but I should check. Thank you.
Okay, thank you.
So,
any other questions?
So if not, I would like to thank again all of the speakers and all of the participants of the session. Sorry for the technical issues in between. And all the speakers are available on Slack, so you can continue the conversation there. And thank you very much for attending.
Thank you.
Thank you. Bye.
Bye-bye.